Is my screen up there? Is there? Can you see the screen?
Yes, we can see.
Everybody's here, I think.
I think so.
Okay. Is everybody ready? Everything okay? Everybody can see the screen, right?
Yep.
Okay. Let's see. I put up a new language. We've been playing around with a little bit with Lisp or with Scheme, and I added lists to language 8 to create language 9. So language 9 is essentially a baby version of Scheme. And what we're going to do is we're going to see that what we can do, much of what we can do in Scheme, we can actually do in language 9. It's not by any means a full-blown implementation of Scheme, but it's reasonably close. It's interestingly, it's interesting what language 9 can do. Like the example of map reduce that we did last week, we could do map reduce in language 9 now if we want to. Okay. Now, right now we're actually kind of doing 2 or 3 things at once. We are talking about language 8, which added closures to language 7. Okay, so closures were this is what makes functional programming, it's one part of what makes functional programming so famous. Right? So we want to explain what closures do for language 8. Now, we've also started talking about Scheme a little bit, just so you could see a real language that uses real closures. Because Scheme is very much a very famous, important language that's quite a bit in use, especially in research. Okay, so we're talking both about language 8 and closures and Scheme and closures. So we're kind of doing these two things in parallel, using Scheme as an example of a real language that does what we're doing in these baby languages. Okay, now the last thing we did last week was we were looking at these examples that let's see. Okay, we're looking at this example, this make adder example. Okay, which is a very famous example. You see it used over and over again. Okay, so we're looking at this make adder example, and we started going through what it does when you run it. Okay, and if you run it with essentially language 7 way of thinking, which is the way of thinking of a language like C and C++ and Java, you run into a problem. And let's see, we had some notes. Do I have them? Let's see. I think they're, yeah. Here are the notes that we were working on. Okay. Here's make adder written in 3 languages. Well, here it's written in Scheme, here it's written in language 8, and here it's approximated in language 7. It can't really be written in language 7 because language 7 doesn't allow these nested lambdas. The key idea here is that we're using what are called nested lambdas. Okay, right? So this function is a lambda. It takes in a single parameter, and it returns a function. So there's 2 things going on. There's a nested function, and it's the return value. So we're returning, if we put it in a comment, we're returning a nested lambda. So there's 2 things going on, returning a function, which is a bit odd, and having a nested lambda. And what makes this really tricky is this X, returning a nested lambda with a non-local reference. The X here is not part of this function. It wasn't defined inside this function. In this function, there's only one parameter, y, and that's this. So y here is bound to that y. But this x is that guy's parameter. So we're using nested scope here. You look in the outer scope for that x that's not local to this function here. Okay. Now that x is the key heart of what's that's strange here. Okay. Now, if you write it in our language, it looks almost the same thing. We're defining a function, make adder. It's a lambda expression that returns a lambda expression, and inside that lambda expression is a reference to that variable that's not part of that lambda expression. Okay. And then we create a variable of type make adder, and then we apply it. Oh, okay. Up here, the scheme part for that would be, you would say define add for make adder for. Okay. And then we would call add 4 on 5. Okay. So these two lines here are the equivalent of those two lines there. Okay. So there's the scheme, and language 8 and language 7, but language 7 is just an approximation. It doesn't really do, it can't do what these two do here. Okay. So these two do the same thing, which is slightly different syntax. Scheme and language 8 just do the same thing, but with slightly different ways of writing it. Okay. Now, what happens when you try to run it? Okay. Now, we're going to run it thinking like it's language 7. Okay. So when we run this, the first thing we do is put this lambda in the global environment. Okay. So first, we execute the thing that puts the lambda in the global environment. Let's see. Oh, I forgot to, yeah, see, the global environment should show that we have, which is got the value of, so the global environment has make adder, which is lambda. I forgot to put that in there before. Okay. Okay. So we're defining, see, you can either do it in scheme using define, or you could use it in our language using fun, but we're putting something in the global environment. We're defining make adder, so make adder is in the global environment. Okay. Okay. So that's the first, that executes that piece of code, which is the same thing as executing that piece of code. Okay. Now we define something else. So now we're going to add 4 to the global environment. Okay. But to define add 4, we have to call make adder. Okay. So now we're calling make adder. Okay. So when we call make adder, we bind his local variable to 4. Okay. So that's the binding of x to 4 in calling of make adder. Okay. Then make adder returns a lambda to add 4. So now add 4, let's see, and when we're done, the global environment's got 2 things in it. Okay, the global environment has got these 2 things in it. Okay, the global environment's got make adder and add 4. Okay, right. So we've now executed this line and added it to the global environment. We've executed this line and added it to the global environment. Now notice at this point, the local environment that held the 4 is gone, because when you call a function and then it returns, the local environment goes away. So now we've got the global environment with make adder and add for. Okay, they're both lambdas. Now we're going to apply add 4 to 5. Okay, so now we're going to do the third line of code, this line of code here, which is the same as this line of code here. Okay, so now we're going to call add 4. So, oops, and I made this little mistake. So the global environment includes that guy. Okay, so now we're going to call add 4 with parameter 5. So we make a local environment that binds 5 to add 4's parameter. Add 4 is, uh, um, yeah, it's this y. That's his lambda. Add 4 is this lambda here. So we bind 5 to y, okay? But then we go in and evaluate the body of the lambda, and that's where things blow up. When the interpreter tries to evaluate the body of the lambda, the interpreter finds that the x variable doesn't exist. You get an undefined variable. There's no x in the environment right now. We're working in this local environment, which is tied to this global environment, but there's no x variable. Something has gone wrong in our way of thinking about how functions should work. This kind of nested function doesn't work with our way of doing things. The key thing is this local environment here can't be lost. We need to find a way to make that local environment not become lost. Okay, so let's start talking about what language 8 and what scheme need to do to make this little chunk of code work. Notice it's a real tiny little chunk of code. It's just essentially 3, 4, or 5. It's all 1, 2, 3, 4, 5 lines of code, but it's 5 lines of code that completely change the language entirely and make the interpreter, and if we were writing compilers, make the compiler it makes the interpreter a little bit harder. It makes compilers way harder. This was a real stumbling block in these languages. Compiling this language was not easy. Okay? But writing an interpreter for it is not hard. We're going to do it right now. We're going to see what steps it takes to write an interpreter for this. But interpreters are very slow. Writing a compiler for this was really quite a bit harder. A lot of research went into how to write a compiler for this. It took a lot longer to write compilers for this than it took to write compilers for a scheme. I mean, compilers for C and C++ and Java, I mean, they've been around since the 60s. Compilers for this, I think, pretty much were the 80s and 90s when they started figuring out how to really compile this. Okay, the key is that we have to somehow not let this environment, which is the one that holds the 4, go away. Okay. All right. So the thing is, we have to add closures to the language. Now, the reason we need closures is because if you take this guy here and you isolate him, so that's if you isolate him, you see that he's not a closed expression. He makes a reference to a variable that's not in this expression here. Now, if you did this, it's a closed expression. See, because now both those variables are bound to here. If you did this, it's a closed expression. Okay, there's no reference to a variable that's not bound in here. Okay, but if you did this, of course, it's still closed compression. But if you do this, now where's x come from? Okay, you need something to close this expression, something that says where to find x. Okay, now x we know exists in some environment. Okay, so what we're going to do is we're going to see a closure will be a lambda expression, and an environment paired together. Okay, so we're going to form a closure by taking this lambda expression and somehow tying it to an environment that holds x4. Okay, so we want to somehow tie a lambda expression to an environment. We want to bundle a lambda expression and an environment together. Okay, well, so we're going to create a new data structure, and the new data structure is going to be called, let me go to the folder for language 8. We're going to create a new data structure. The new data structure is called a closure, but I called it in this language an IPEP. So there's the data type, IPEP. And it's a closure. What I get, IP stands for instruction pointer, and EP stands for environment pointer. Okay. And so the closure is, so a closure is an IP EP pair. It's a, because IP is really, it's a fancy word for lambda. An IP is something that points to your code, and that's what a lambda expression is. Lambda expression is the code of the function. So the IP EP pair is like, it's a term that people used a long time ago, and I think it's kind of helpful because closure and IP EP pair are synonyms. Closure is, they're both good terms. Closure helps you remember that what we're trying to do is close this environment so that it doesn't have unreferenced variables. Okay,
And
so it doesn't have
IPEP
undefined variables.
tells you how to
So
do it.
we're closing the environment. But it's also worth remembering that what we're doing is we're pairing a code that has a non-local reference with the environment that says, here's how to look up that reference. Okay, so there's the code with the non-local reference and the environment with the local with the holds of the value of the local reference. So we're pairing an IP and an EP together. So closures are pairs. Okay, and it's a instruction pointer and a environment pointer. Then if you look in here, the IP EP pair is just a real simple data structure. The IP is a tree, because that's what code is for us. Code is something in the abstract syntax tree. And the EP just is a pointer to an environment object. Okay, so all this is just a data object that holds nothing but those two references, a reference to the tree and a reference to an environment. Okay, so this is a closure for us. This simple thing here is a closure. Okay, now how are we going to use
Hello?
it? Okay,
Hello?
we go back here. Let's see, go back here. The key is what's inside the global environment. When we had a function, we pointed to its lambda, which is the IP, right? That's the instruction pointer. So all these lambdas were instruction pointers. Okay. We had all these lambdas in our environment that are instruction pointers. What we're missing is the EP. We need a IP-EP pair. Okay, so what we're going to do is, instead of storing in the environment a pointer to a lambda expression, we're going to store a pointer to an IP-EP data structure. Okay, the value of a lambda, the value of a function in an environment is going to be an IP-EP pair. Okay, so when you define a function, the value of that function is no longer the lambda it points at. The value of the function will be the lambda it points at, but an environment also. And we have to learn the rules for what the environment should be. Okay, so every function now is going to carry an environment around with it. A lambda expression is not, a lambda expression is it's kind of tricky. we think functions are lambdas, but what we're really doing is we're saying functions aren't lambdas, functions are more than lambdas. What we mean by define a function is you have to tell me what code you want to execute and what environment closes the code you want to execute. When you define a function, you have to tell me two things. The code is going to be explicit. The environment that goes with the code is going to be implicit. Okay, so, and we're going to set the rules for what the EP is. But from now on, a function is two things. The code you want to tell me to execute and an environment that tells me where to find the undefined variables. So for example, you might think this is a function. Whoops. Like if I use math notation. Okay, that's a function mathematically, but it's not going to be a function for us because it's missing where do you look up the y. Okay, so what would make this a function is to bundle it with an environment holding, say, y3. Okay, now that pair is a function to us. That pair is going to be a function. The code and the environment from wherever it came, we have to say where it can come from, but an environment that says, oh, when you evaluate this function, here's where to look up the environment. Now, what's interesting is that and those are two different functions. Okay, because this this says that it's this function paired with this environment. This one says that's a function paired with a different environment. So these are actually two different function values. Now that's real different than from the C point of view. From the C point of view, that there is no environment associated with it. You just have a function. So this function and this function are the same. But in our new way of thinking, this pair is a function, and this pair is a function. Though calling them functions is a little bit confusing, we should probably call them closures. See? So this is a closure, and this is a different closure. But people really blur the distinction between closure and function. It should be that a closure is two things, a function and an environment. So this is a different closure because it's got the same function that this one does, but a different environment, so that makes it a different closure. So this closure is not the same as this. So if you use the word closure, this is one closure and this is another closure. Unfortunately, people use the word function essentially as a synonym for closure, and then things get really confusing. Is this one or two, is this the function? Well, not really. This is the function. But if this is the function, what do you call this inside of the function? And that's where people get trips up. They'll call this guy the function, and they'll say, oh, and this guy's the function too. If people are really, really careful, they'll say this is a function and this is a closure. And that this is the same function, but I'm using it in a different closure, so I have that these are not the same closure. Notice that this closure can be evaluated. This closure, actually, this closure can't be evaluated. This closure can be called. Okay, so let me call this closure 1 and call this one closure 2. Okay, if I apply closure 1 to 6, that's different than applying closure 2 to 6. Okay, because one will give me back 9, the other will give me back 10. So this would bind 6 to the function parameter, but then use the environment to look up the unbound variable. This one would bind 6 to the function parameter, but then it would use that environment to look up the unbound. So I'm not calling a function anymore, I'm calling a closure. Okay. Now, but the notation we use is kind of, okay. This notation is not used by any language. We still would say you apply a function here and a function here. The question is, like, how do you separate these two closures? Okay, how do you denote these two different closures? Okay, and that's what we have to get at. This is the idea, but this idea is pretty good explanation of what's going on, but it doesn't look like the kind of code we're going to do. You know, nobody writes their code like this. Nobody writes a function paired with an environment and then writes a function paired with an environment. Like, you know, I could write another closure 3. Here's closure 3. It could be a g of y equal to x times y plus z. And then it's paired with an environment that has, well, there's two unbound variables here. So I need x bound to something, and I need y bound to, and z bound to something. Okay, there's another closure. You know, the closure is some function and an environment that closes the function. So an environment in which you can look up any variable that's not one of the parameters. Okay, and then I could, you know, apply closure 3 to some parameter. Okay, so we should be applying closures, but nobody really thinks of it that way. We call functions. We don't call closures. We call functions. But the truth is, you know, you have to think of it as every time you think you're calling a function, you know, instead of like, you know, here we'd have f, g. Okay, these are ambiguous. You really can't, you know, there's something wrong here, because when you call f with parameter g, you don't, you know, which one are you doing? Is it the f that's with this closure, or is it the f with this closure? Okay, yeah. So, you know, but this is the kind of, we use this kind of terminology all the time, but what we really should be thinking is this: we should be applying closures, you know, and a closure is a function with an environment. Okay. Okay. Now, over here, we solve this problem we solve this problem by essentially attaching, by when you define a function, so you put that name in the environment, we put a pointer to the lambda and a pointer to the closure and a pointer to the environment in the environment. So the environment essentially has both of these always attached to them. So a function name is always going to be from now on attached to two things: the body, the function definition, and the environment. So the environment's going to end up being implicitly tacked on to every function name. So we'll still use function names, like here, I'll still say call add4, but I'm really not calling add4, I'm calling a closure that includes add4 and some environment. Yeah, and here I'm applying, see here I'm calling makeAdder. Well, what I'm really doing there is I'm calling the makeAdder function, but with some environment. I'm really calling a closure here, not calling a function. I don't know if anyone's ever come up with a better notation for this. I don't think anyone would want to have, you know, saying apply a closure. That really wouldn't work, and you know, that would cause all kinds of confusion in its own right. But the way the languages do work, like Scheme and Lisp and all the modern functional programming languages, you have to remember that every time you see a function call, you're not just calling a function, you're calling a function with some closure attached to it. And if you see the same name, that doesn't mean that that function and that function really are the same function. They could possibly have different closures attached to them. Okay, and we'll see how that could happen. That it could be that this name, it would have to be that that name is in more than one environment. If the name is in an environment like here, see, that name gets attached to just one closure. Okay, so that name is a closure. So when I call this function, I literally am calling a closure. Yeah, so I really am doing this, not this. We really are doing this, not this. It's just that the closure is bundled into that name there. Okay, so the name of a function actually is really the name of a closure. The names of functions are really the names of closures. Whenever you define some name to be a function, you're really defining it to be a closure. Okay, so this is kind of tricky. Okay. Now, what we're going to do then is now let's go through and see how this thing kind of fixes. Okay, all right. When I define this function here, okay, this function actually, let's see. Oh, okay. This function here is closed. Okay. Notice that there's no variable in here that's not referencing anything outside of it. You know, this x is to that x and this y is to that y. This is a closed expression by itself. Okay. So when I define make adder is defined to be this guy here. That's closed. Okay. When a function is closed, its closure, its EP is to the global environment. Okay. You just link closed expressions, their EP link to the global environment. Okay. So here, when I call make adder, its IP/EP will be the lambda and the global environment. Okay. So make adder is closed. Okay. So its IP/EP is the lambdas, that guy. And then its environment just is the global environment, which is this guy here. It just points right back to this guy here. Okay. And you could even make this null. You could actually, I don't even, maybe that's a better idea. You could make that null. Since this guy is closed, it doesn't need a global environment. It doesn't need a second environment. So for now, actually, I think we can just say it's null. So the IP is the lambda and the EP is null, okay? Because this thing here doesn't have any variables that you have to look up somewhere else, okay? All right, now we get to this guy down here, okay? So you're gonna, oops. Now we're executing the code that is defining add4. Okay, so we're trying to put add4 in here. Okay, so make adder has actually, to make things a little bit easier to read, call this lambda 1 and this lambda 2, just so that we can say that this is lambda 1 here and this is lambda 1 with a null environment, and this IP/EP is going to be lambda 2. Okay. See, when we define add4, okay, when we define it, we have to call make adder with parameter 4. Okay, so we create a local environment which holds make adders x bound to 4. Okay, and we jump into make adder. Okay, then make adder is going to return lambda 2. So add4 is going to be pointing at an IP/EP with
Hello?
lambda 2, okay,
Hey.
because we call
Hi,
add4.
Professor.
I'm sorry, we're defining add4.
He can't
So that
hear
means we
us.
call make adder
His
with
system is
parameter
muted.
4. We
Okay.
create the local
Yeah, I've been
environment
trying to get his attention for like
for
20
this
minutes.
His speaker
expression
is
here,
muted.
lambda 1. Then we
Yeah,
evaluate
check it
lambda
on
1. Lambda 1
Bottom left-hand
returns
corner.
Lambda
See
2
that?
to
Yep.
us.
Yeah,
So it returns
it is
Lambda 2,
muted.
but it has to return a closure. It's got to, we
And he's
have
not
to
reading the
specify
message as
now
well.
what
Nope, he
goes
is not.
in here.
He's not looking at the video
Okay,
either. I've
what
waved
goes
to
in
him
here?
plenty.
Yeah.
Well, what goes in here is a pointer to this guy here. See that local environment? I'll call this local environment 0. Okay, so that's local environment 0. That's the that was the first local environment we created. This guy is what becomes the EP in here. Okay, this is the tricky part. This is the part that makes this work. When this function is called, when makeAdder is called, you build a local environment to hold the local parameter of makeAdder. That's X. That's the environment that was going to go away when makeAdder returns. But that's the environment that we really want to hang on to. So what we do is we bundle in the return value of makeAdder, the IP-EP pair. The IP points to Lambda 2, okay, because that's where the code is. And the EP points at this guy here. Now, this guy doesn't disappear now because Java is a garbage collected language. That object, that environment object, now has a reference to it. Since
Yes,
that
I know.
environment object has a reference to it, that environment object doesn't get
Let me
garbage
see.
collected.
Annotate.
So now it just sort of hangs around
Draw.
in memory. Okay, this function returns. Okay. Oh, let's see. Oh, I have my speaker off. Did somebody say something? Yeah. Okay. I did the same.
A
Yeah, I have
couple
my
were
speaker
saying-
off
people.
again. Okay. Okay. What? You have a question?
I had a question of what was the difference between closures and objects?
Oh, closures are. There's a real subtle argument about that. See, right, think about it. A closure is code with data, right? And that's exactly
Objects
what
are also
code
code
with
of
data.
object.
Yeah. There's a whole bunch of kind of jokes about this. You Google poor man's object, and you get closures and object equivalent, closures of poor man's objects, and objects of poor man's closures. They're two sides of a coin. You can implement closures using objects, and you can implement objects using closures. And this led to object-oriented functional programming languages like Scala and JavaScript. And it's a compelling argument because a closure is a pointer to code, which would be the methods you think of. But see, there's one big difference. A closure is a pointer to one method and data. An object is a pointer to an arbitrary collection of methods. Okay, so an object's a little bit more elaborate than a closure, because a closure really is saying there's one function and some data that goes with it. Then that function acts on that data. An object says, I've got some data and a bunch of functions that act on that data. So that's one big difference. But it turns out that you can implement closures with objects, and you can implement objects with closures, and you can turn any functional programming language into an object-oriented language, but you can't turn any object-oriented language into a functional language. So if you look at it from the right point of view, functional languages are more general than object-oriented languages. Closures can be used to build objects really easily, and you can turn any functional language into an object-oriented language. It's a little bit harder to go the other way, though we're doing it here. Notice that we're taking Java we're using Java to write our interpreter. So from that point of view, you can say I'm turning Java into an object-oriented language. The Java language is now running an object-oriented language. The Java language is now running a functional programming language.
There's a saying that any sufficiently complicated program just starts to look like Lisp,
That's where this came from.
which is
Yeah.
also what we're doing.
Yeah.
Funnily enough.
Exactly. Yeah. That's we're building Lisp inside Java. Yeah. But it's actually a very good thing to realize that closures and objects have a lot in common, because a closure is a pair of a little bit of code and a little bit of data. And that's exactly what an object is. It's a pairing of code with data. But object-oriented programming really emphasizes that. And so it lets you put as many functions. You can have an arbitrary number of functions bound to your data. Okay. Now, we will build. That was one of the things we'll do in the next couple of weeks. We'll see how in Scheme you can build a baby object-oriented programming language. We will build objects, okay? And we'll see how we can do that using closures, okay? All right, so back to over here, when the interpreter is interpreting the language, the key is that when the interpreter puts a function in an environment, it actually puts a pair of things in the environment: the pointer to the code and a pointer to the closing environment. And if the function already is closed, the environment can be null. Okay. Now,
hi, Professor. I have a question about the top code, the code on the top.
Yeah.
The Scheme one. Define make adder. I think Lambda is a keyword. You can change it to Lambda 1.
No, you can't. I did that there because I want to say that this is a pointer to that piece of code, but this one's a pointer to just that piece of code. And I couldn't think of any better way to do that than to just like pretend that this is Lambda 1 and pretend that this is Lambda 2.
Oh, so this is not Scheme code. It's just some
right.
code.
Yeah, now it's
okay.
Yeah,
right.
Yeah, so it was I was trying to think. I mean, I can't draw arrows here. Yeah. So really what I want is an arrow from here pointing to there, line 4. Okay.
Yeah.
And I want an arrow, like actually, what if I put line 4?
I mean, you can do that.
Well, I mean, I could, but I'd have to save it as a JPEG. Yeah, I mean, using the annotation.
Yeah, like this. Let me make sure I'm gonna point.
Well, actually,
the right
but I could also
thing.
do it just. I think by just and then say like line 5 here. Yeah. See that gets, maybe that's a better. This is not a bad idea either, because then I don't have to mangle the code up here. Okay. So what's the code pointer? The code pointer is to line 4.
Oh.
See, code points to line 4.
Right? I mean, that sounds fine to me, because that might even be your underlying representation of what is in there. It might point out.
Well, we're going to point to the abstract syntax tree. So we'll be pointing to a node in the abstract syntax tree. Remember the IP-EP pairs. Literally are
pointers to trees.
Yeah. See, they point inside the abstract syntax tree. So they point to the code by pointing inside the abstract syntax tree of the program. So I would want this guy here. I'm sorry. I would want this guy here, this one that says line 4. It should be a pointer to that node in the abstract syntax tree. And this one that says line 5 would be a pointer to that node in the abstract syntax tree. Okay. And then this one is a pointer to, well, this one's null, because line 4 is a closed expression. There is no unbound variable inside that. So it doesn't really need a closure, so we can say its closure is null. But line 5 is not closed. Line 5 makes a reference to something that's outside that lambda, okay? And what closes it is the environment that was created when that function was called, okay? Right. Now, okay. Now, when you get to the next line of code, when you get to calling add for, now you're calling the closure. Okay, when you call add for, this is here's what's going to happen. Okay, we get down here when the interpreter finds that X is not local,
It'll hop up one level in the environment table.
no.
No?
Well, let me finish here. Okay. When the interpreter is evaluating this lambda, okay, so it's evaluating this lambda here. See, it's add 4, which points to line. I'm starting to run out of room. It points to line 5. Add 4 points to line 5. So it's evaluating that lambda there. When it evaluates that lambda, it hits an undefined variable x. So it looks in, it does not hop up here. It actually, well, it goes to that environment there. Because it's evaluating add 4, and add 4 says when you don't find something in the local environment, go use this other local environment. Okay, so this local environment includes the binding for add 4's parameter, but then add 4 has the closing environment. So if finds when it finds that X is not local, it looks for X in the closing environment. Okay, the closure. Okay, it looks for X in the closure. So that means it goes to add 4, looks up its entry in the environment, finds the EP pointer, and then that points it over to this guy. So see, this guy's going to still be in memory. So then the X is gotten out of that guy there. So this guy points to local environment 0, which is this guy here, and then that variable gets found. This one, when this function returned, this was not garbage collected because there's a variable pointing to it. Then when we need it, when we're evaluating add 4, we build the local environment to evaluate add 4 like we do with most functions. But then when we find a non-local reference, we go to him and say, okay, what's your closure? And then we get a pointer to there and we get the closure. Okay? All right. So every function carries with it its closure. Functions carry their closure and you're really applying their closure. So the functions, we can now think of them as these, the functions are these kind of things. It's a code and a environment bundled together. Okay. All right. So now this is the repair job of the example. I mean, this is a rough sketch kind of. Oh, and then language 7, we can drop that from this picture. Actually, in this picture, we don't need the language 7. Okay. All right. So that makes it easier to see the whole thing. Okay. So we can think of it as either in terms of the scheme code or the language 8 code. They're exactly the same thing. You can think of it as either one. Okay. But when you evaluate that line of code, so that's the that's okay. Yeah. So when we evaluate this line of code, well, actually, well, if you think about it, there's 1, 2. I'm sorry. There's 1, 2, 3 lines of code in here. Just like there's define as one line of code, define as a second line of code, and this is function calls the third line of code. So the first line of code, if I do it carefully, the first line of code is the define make adder. Okay, so first you do that, and that builds this global environment. Okay, so that gives you the global environment. Then the second thing you do, okay, so the second line of code, so you do the first line of code, that builds the global environment. That puts make adder into the global environment with an IP EP pair. Okay, then you're going to evaluate the second line of code, this line of code. Okay, I'll type it as okay. So evaluate this expression. Then you'll create the local environment hanging off the global environment. Okay, and then that'll be the function call. Then when the function returns, this is while the function's evaluated. When the function returns, you end up with that global environment. Okay, the global environment has two functions in it now, with two different key value pairs. Then you're going to evaluate this expression, which is, if I switch to the scheme version of it, you apply that expression. Okay, this is the tricky part. When you evaluate this expression, you look up add4 in the environment. You see that it's got its lambda expression at line 5. So you can go to line 5 to get the lambda expression, and you know where its environment is. Its closing environment is over here. Okay, you build a local environment. You evaluate this lambda expression in the local environment, except that when you don't find something in the local environment, you don't go up this way. When you don't find something in the local environment, you go over to this one. Okay, you go over to that environment there. Okay, so you evaluate it in the local environment along with that closing environment. Now, yeah. So let's look at how this code gets written in the interpreter. Okay, so let's look at what the interpreter does to do this. There's two things we have to look up in the interpreter. What happens when you define a function? Now, notice you can define a function with fun. In Scheme, you use define. In our language, you can use fun instead of define, or you could use var. Okay, you can define a function with either fun or var. Okay, and I just left it. They're exactly equivalent. Fun and var are equivalent. It's just fun is left over from language 7. And now in language 8, since functions are arbitrary values, you can use var to define functions along with. Remember, fun used to be only at the top level. So it used to be fun existed only at the top level. Now in the grammar of language 8, fun can be anywhere, just like var can. So fun and var become equivalent. So yeah. So remember, the fun and var are now really the exact same thing. The only difference is that var can define any expression. Fun only defines lambda, but lambda is an expression now. So fun is just a special case of var. Var says you can define a variable to be any expression. Fun says you can define a variable to be only a lambda expression. But you can use var to define lambda because lambda is one of the expressions. So var is just fun is just a special version of var now. And it doesn't play any special role. It doesn't have to be any place specific. It is kind of useful. A lot of people like having a keyword like fun in the language, because when you read code like this, it's sometimes good to say that, oh, we're defining a function here, not just an arbitrary variable. We're defining a function. So many functional programming languages, they have a keyword for defining functions that's redundant with the keyword for defining variables. And in Scheme, they use the same keyword for both functions and variables. So you just have one. So define in scheme is like there in our language. It defines something, and it can be used to define either a function or an arbitrary variable. So scheme only has one word, define. Many languages do have both a function word for defining functions and var for defining arbitrary variables. But in that case, the fun and the var are just redundant. Well, fun is redundant with var. Okay, so we have to say, since fun and var are the ones that put something in the environment, since they're the ones that put the key value, since they're the ones that put the closure in the environment, we have to look at how they do that. So we have to look at how fun and var put a closure in the environment. And then we have to look at how apply uses it. Okay, so we have to look up really two things in our interpreter to see how this works. How does a closure end up in the environment? And then how does apply use the closure in the environment? Okay, so look at the code for evaluate. Okay, so let's look up evaluate fun first. Oh, okay, so find it. Let's see, I skipped out. Where's evaluate fun? Oh, here. Oh, see, here it is. Okay, so here's evaluate fun. Actually, I could have just said evaluate fun calls evaluate var. I really could have just because they're going to end up doing pretty much the same thing. So I really could have just had evaluate fun just make a call to evaluate var. Let's go through here. So you get the function name. Okay. So yeah, you're looking at a fun abstract syntax tree. It's got a left branch. It's got a left branch that is the name of the function. Okay. So you get the name of the function. Okay. You do a little check. You can't redefine, just like any variable, you can't redefine a variable. So if the function name is already defined, you throw an exception. Okay, so you can't define a function in the same scope more than once, or any variable. Okay, now this part here is a little bit, this is where evaluate fun is a little bit different than var. If you're going to say evaluate fun, it checks that you're really defining a lambda. Okay, all right. So evaluate fun does check that it's being used to define a function, whereas evaluate var can define anything. Evaluate fun should only define functions. So this is what makes evaluate fun different than evaluate var. It checks that the right-hand side of the fun abstract syntax tree is a lambda. Okay, all right. Now suppose that if those two tests are passed, okay, you build the parse tree. No, you evaluate. Let's see now. Oh, you evaluate lambda. This is what builds the closure. Now normally there's nothing to do in evaluate. You don't evaluate lambdas. In the earlier interpreters, we didn't evaluate lambdas. We just pointed at them. But now we have something called evaluate lambda. That's actually a new thing. It builds the closure for us. So the code that decides what the closure is going to be, which is, part of the closure it's a lambda. So half of the closure is the lambda, but the other half of the closure is the environment. So the code that decides what the closure is going to be put inside evaluate lambda. Okay, so this result is going to be a closure value. Okay, so now if we look at our values, we see that value now has a new kind of value. Okay, see, there's the new kind of value. a value now is either a string, an integer, a Boolean, or an IPEP. See, it used to be a tree. I left the old code in there to see what changed. A lambda value used to be a tree. Now a lambda value is an IPEP pair, a closure. Okay, so we've switched from representing functions as just pointing into the lambda expression to being, well, you have to point at a lambda expression and point at its environment, its closing environment. So this guy now holds the the tree is sitting inside there along with the closing environment. Okay, right. So the value class has this one little change here. That's the only change made into the to the value class, is that instead of a lambda value pointing at a tree, the lambda value points at an IPEP. Okay, so then we build the closure value by calling evaluate lambda. Okay, and then once we have the name and the IPEP, we just stick it in the environment. Okay, now evaluate var is going to be pretty much the same thing. Evaluate var doesn't even know that it's evaluating a function. Okay, evaluate var, now think about it if it was pointing at a lambda expression. So think about the case of evaluate var when var has got a name and then something that returns a lambda expression. So now we have var name, something that could return an expression that returns a lambda expression. So think about what's happening here. The var has two branches, the name and the value. Okay, get the name. Okay, check that the name's not already been defined, so you don't have a redefined variable. Okay, now you get and evaluate the right-hand branch. The right-hand branch might be a lambda expression. So this result could be a Boolean, an integer, or a IPEP closure. Okay, so in the case of over here, when the var had a variable and something that returned a lambda expression, over here, that's stored right there. That guy's the lambda expression. The lambda expression, well, that guy's the closure. And the closure includes the pointer to the lambda expression and pointer to the environment. So then you just add it to there. Okay, so this thing takes care of any kind of expression, where the expression returns a function or if the expression returns an integer or a Boolean. It handles, this is now very general purpose. It handles any kind of expression. So it handles expressions like this. Var add 4 is the which here we know that the result of applying make adder to 4 is that lambda expression. So we're going to get back var is going to be pointing at a closure representing that lambda expression. Okay, and that's actually handled by evaluate expression. But evaluate expression could be evaluating a lambda expression. Okay, so now let's evaluate a lambda expression, because evaluating a lambda expression is what returns a closure for us. Okay, and evaluate lambda is just one line of code. It's actually kind of, it's amazing. We're in a world where one line of code can take you a week to figure out. Okay, this is where you get to the real serious programming, is when you're doing something profound and you say, oh, my profound line of code is this. One single line of code that creates the closure. Okay, so what does it do? Okay, the closure, when you're building when you're creating a closure, you're given the lambda expression, and you're evaluating that lambda expression in that environment. That environment is the closure of that lambda expression. The tricky thing is to realize that the only way you get to this is if that tree is closed by that environment. Okay, over here, it's what it was we were in this environment. We were in this environment when we called evaluate lambda right here. Okay. See, the function returns that expression. See, that function returns that expression. So you have to evaluate that expression. So you're evaluating a lambda. So now when you evaluate that lambda, you evaluate it in the environment of the function. So you're evaluating that lambda in that environment. So the closure is that lambda with that environment. So over here, when you're called to evaluate a lambda expression, you're evaluating that expression in that environment, but that expression is the lambda environment, is the lambda expression. So you create a pair of the tree and the environment. I don't think this is trivial. I mean, I don't think this is just super easy to understand. I mean, it took me years to get used to this, but this is really a profound thing. This is just one line of code, and it's doing something really amazing. You know, it's creating the closure, and it's just tricky to realize that whenever you want to evaluate a lambda expression, this guy, the expression you're evaluating is this tree. You don't do anything with the tree, but remember where it is. And you know, the environment you're evaluating this tree in is the environment that would close that tree. So the closure is the tree and the environment. Okay, so that's all there is to evaluate lambda. And notice that I've got 20 lines of explanation for one line of code. Read it, you know, read the explanation, think about it. It's not a joke to say that, you know, this one line of code needs that much explanation. Probably actually needs more than that. You know, this is just, you know, this is a summary of the idea. That one line of code needs all that kind of explanation. Okay. All right. So now we've got, in terms of the evaluator, we can evaluate a fun. Okay. When we evaluate a fun, we define a variable. We define that function to be that lambda expression. When we evaluate that lambda expression, we the fun just becomes, you know, it's wherever you evaluated that fun, its closure is wherever you were wherever that lambda was when you called fun. That's where its closure is. Its closure is where it's sitting. Okay, its closure is the current environment. Okay, so okay, here's evaluate fun. We're evaluating fun in some environment. Now this could be nested in anywhere. We could be, you know, so this environment doesn't have to be the global environment, but we're creating a function object. Here's the tree of the object, and we're currently in this environment. Okay, so we evaluate lambda. There's that tree, there's that environment. So whenever you call create fun, wherever you are in the code, whatever the current environment is, that's the closure for the lambda expression. Okay, so over here, now remember make adder, I said you could have this lambda expression be null, but in fact the way we just defined it, it's will be the global environment. Okay, because when this is being evaluated in the global environment. See, this is the very first line of the scheme program. So this lambda is being evaluated in the global environment. So in fact, that make adder, his closure is the global environment. Okay. Now he doesn't really care. He doesn't even need the closure because he's a closed expression. So an interpreter could possibly notice that this is a closed expression, so it doesn't need an environment. But the way we wrote the interpreter, this one will actually be the global environment. So this one will be the global environment, okay? Because whenever you're calling evaluate fun, you build the lambda expression with whatever environment you called evaluate fun with. That environment is the environment. Yeah, even So it doesn't matter if it's open or closed, it will close it with the global environment. Okay. Oh, if I went over here, I could make that need to be the global environment. Okay. Like, suppose I just did make a little minor change to here. Now I created a global variable, right? There W is 2. Go ahead and put that global variable in there. Okay. Now there's
Wait,
two.
Is that a global variable though?
Oh no, I put it in the wrong place. I'm sorry.
Oh,
Yeah.
okay.
Yeah, I meant to put it. Thanks. Yeah, I meant to put it in the line
Okay.
above. Yeah. Okay. Or yeah, I meant to put it in the line above, which down here would put it there. Okay. All right. So now I got a global variable. Okay. Now this guy's closure better be the global environment, because now he needs to look up one variable one place here. Notice that now he's got 3 different kinds of variables here. Y is local. X is from the nesting scope, and W is from the global scope. Okay. So W would be from up here, and X would be from down here. Now, that's actually kind of interesting, because this W will be gotten because this environment points to here anyway. Yeah, we'll do more examples. We'll do more examples as we go along, because there's a subtle difference between this X and this W and a global variable. Like what if this one didn't have that? I'm sorry, didn't have like that. Okay. Now it doesn't reference this guy. It only references the local and the global. So there's different kinds of patterns that can come up here between referencing a local variable and a global variable. Okay. So we'll do examples of that. There, back to where we were. Okay. His closure is the global environment, because that's where he's sitting in. Make adder sits inside the global environment, so his closure is the global environment. We could have said his global environment was null, his closing environment is null, because he actually is a closed expression. But the way we've written the interpreter doesn't work that way. The interpreter will just go ahead and use the same rule, that it doesn't check to see if the expression is closed. If the expression is closed, compilers do this. If the expression is closed, it doesn't need a closure. So that's an optimization they can make. If a function is a closed function, it doesn't need a closure. But our interpreter is not going to be as fancy as a compiler, so it will always use a general rule that always works. In this case, it'll say, well, you're sitting inside the global environment, so your closure is the global environment. Even though you don't need a closure, I'll give you a closure. So this guy gets a closure even though he doesn't need it. Okay. Right. So we've seen now how evaluate fun along with evaluate lambda create the closure. And we run out of time, but then what we'll do is evaluate apply is going to use the closure. Okay. So we're going to see now how the steps to evaluate apply, there's a subtle little change in the steps here. It's not much. There's like one little change between language 7 and language 8 in evaluate apply, which makes this thing use the closure. One last thing, if you compare the interpreter to language 7 with the interpreter to language 8, there's only 3 or 4 lines of changes. Even though the language is profoundly changing from a C-like language to a functional language, the interpreter is not a massive rewrite. It's just at some point we'll go through and we'll see there's just a few little changes from language 7 to language 8 in the interpreter that turns it into a functional language. Okay, so I'll put these notes. I've been writing these notes. I'll put them up on the website. If you have any questions, please let me know. We'll see. The homework, there's a program assignment due when?
The 20th.
So, okay. Still a week away.
Mm-hmm.
Okay, I forgot when it was made due. Okay, so if you have questions about the program assignment, let me know. Okay, so that's due the 20th. Yeah, and there'll be one more after that. There'll be one more. There'll be one brief program assignment after that one. Okay, but if you have questions about the program assignment, let me know. And let's see. I'll go ahead and end the meeting now. So let me know if you have any questions. Bye.
Goodbye.